Okay, so in this lesson, we're going to be looking at estimating the mean with small samples. And as you know, in 8.1, we examined samples of size 30 or larger to write confidence intervals for the population mean. And of course, there's many practical and important situations, however, where we don't necessarily have a large sample. It's just not available. So for today, we're going to be looking at forming confidence intervals to estimate the population mean when we have to work with a small sample. So a small sample is defined as a sample where n is less than 30. A large sample is where n is greater than or equal to 30. When we do small samples, we're going to be using something called a t variable. When the sample size is small, we introduce a new variable called the t variable. We're going to use that variable to avoid the error involved replacing the population standard deviation with s as we would with a large sample. So we're really just distinguishing that we're using a small sample, and we're going to distinguish that with the t variable. Unlike our methods for large samples, the population standard deviation cannot be approximated by S, which when the sample size is small, and we cannot use the normal distribution. However, lucky for all of us, we're going to be using generally the same methods as we did in 8.1 to find the maximal error of estimate and to find confidence intervals, but we're going to use the t-distribution. And you'll see what I mean. We'll do some practice. The t-distribution is a probability distribution that is used to estimate population parameters when the sample size is small and/or when the population variance is unknown. If the variance is unknown, that means the standard deviation is unknown because the variance is the standard deviation squared. We also are going to use what's called degrees of freedom. There are actually many different t-distributions. The particular form of the t-distribution is determined by the degrees of freedom. The degrees of freedom refers to the number of independent observations in a data set, and we abbreviate this to lowercase d period f period. All right, here are the steps that we would use to find a confidence interval for a small sample. First, we're going to make sure that we have a sample size less than 30. Then we're going to determine what the point estimate is. It's going to be a given value, x bar. Will be given the confidence interval, just like when we did large samples. We'll calculate the degree of freedom based on n. Remember, n is the number in the sample. Just make a note here, n is the number in the sample. The degree of freedom will be n minus 1. We're going to use something called a t-score, and we're going to be using table 6, which you'll need handy whenever you're doing these problems, and that is on the last page of these notes. We'll use the formula for E given here, very similar to what we did with large samples, only instead of a z-score, and we were looking at z-scores here, we're looking at t-scores for small samples. We'll find the left-hand boundary, we'll find the right-hand boundary, and we'll write the probability statement. All right, so let's do a practice problem. There's two parts to this one. We have a problem involving the weight of artificial sapphires. A company has a new process for manufacturing large artificial sapphires. The production of each gem is expensive, so the number available for examination is limited. In a trial run, 12 sapphires are produced. All right, so let's just highlight, or you can circle. All right, so 12 sapphires. The mean weight for the 12 gems is right here. X bar is 6.75 carats. And the sample standard deviation is 0.33. Let mu be the mean weight for the distribution of all sapphires produced by the new process. So we want to find a 95% confidence interval for this population. In this case, n is 12. The point estimate is asking for x bar, 6.75, and our standard deviation is 0.33. The degree of freedom is going to be n minus 1. In this case, n is 12 minus 1. That gives us 11. The confidence interval is going to be based on 0.95. And now we have to find the t-score. So we're going to go to the last page of the notes, and we are going to be looking at the degree of freedom equal to 11 for a confidence interval of 0.95. So let's go to the last page and take a look at the table. So we want 11, and we want to match that with the 0.95 column. So that brings us to this value right here, okay, 2.201. We're really only going to be looking at this row of the table, depending on, what percent confidence interval we're constructing, and then we're going to be picking the column for the degree of freedom. So we had 12 in our sample. The degree of freedom is 12 minus 1, so 11. And we're looking at a 95% confidence interval. So our t-score, and that's what we're getting out of this table, is our t-score is 2.201. Our error of estimate is t sub c times the standard deviation divided by the square root of n. So for this problem, it's 2.201 times 0.33 divided by root 12. And when we simplify that out, we solve that out, we get 0.21. And everything else is really going to be the same. The left-hand boundary is going to be x bar minus e. The right-hand boundary is x bar plus e. All right, so in this case, x bar is our point estimate, which is 6.75 minus 0.21. That's 6.54. X bar is 6.75 plus 0.21, which is 6.96. So we're going to write our probability statement. We are 95% sure that the population mean is between 6.54 and 6.96 carats. Okay. Now we're going to construct a 99% confidence interval. The degree of freedom doesn't change, but just as a reminder, it's n minus 1. So it's 12 minus 1, which is 11. Our C value is 0.99. So we have to go back to our table 6, and we're going to find the row for the degree of freedom of 11 and C value of 0.99. All right, so that changes all this. Now we're looking at, this keeps going to this guy right here. So we're getting 3.106. E is t sub c times the standard deviation divided by root n. So it's 3.106 times the standard deviation, which hasn't changed. It's 0.33 divided by root 12. That's a point there. That gives us a value of 0.30. The left-hand boundary is the mean, or the point estimate, 6.75 minus 0.3. and that gives us 6.45. And the right-hand boundary is 6.75 plus 0.3, and that gives us 7.05. So in this probability statement, we will say that we are 99% confident, or I should say sure, I don't want to change what I've been writing every time. We are 99% sure that mu is between 6.45 and 7.05. All right, so hopefully you're feeling good about this, and that's all I have for today. Thanks for watching, and I'll see you next time.